Hello and welcome to this manufacturing systems technology module 14. So, a quick recap of the last module. We were actually talking about how to do a surface patch, okay, and we wanted to find out a modality where algebraically we could determine what is the quantum of calculations involved in pointing out to a surface patch. This patch would be used for any complex topology which is not a regular geometry, and it can be varied according to some parameters in a manner so that it fits the actual surface, and that is how you actually represent a surface by mapping it topologically between various patches and interconnecting those patches with respect to one another. Just as you do the curve based fitment of a geometry, you are doing a surface based fitment in this particular case. So, let us look at the surface representation. Just need to extrapolate the curves by another dimension. So, in case of curves, for example, we had seen that the representation of curves were done by implicit and explicit equations. Same thing holds true for this also. So, you can have an implicit equation to describe a surface, just as you had done earlier for a 2-dimensional curve or even a 3-dimensional curve. So, let us say you can have a functional relationship f x y z equal to 0. Its geometric meaning really is a locus of points that satisfies the constraint equation, and that defines the surface, okay, and they are all sort of bound by this functional relationship f x y z equal to 0. So, this is the implicit form of the equation, and it is not very clear as to how there is a relationship happening between x or y or z, although there is an overall governing relationship between all the three variables which happens. For an explicit equation to describe a surface, the same thing can be represented in a more direct manner by looking at independent coordinates x and y, okay, and varying them and studying the functional relationship of z with respect to x and y. So, the z varies as a function of the various x's and y coordinates on a surface. So, that is how you explicitly represent the position vector in this particular case, okay, on a 3-dimensional plane. So, two variables are completely random, and then this functional relationship is a governing relationship between z and the way it goes with the different values of x and y. So, the comparing the equations for a 2D curve and a 3D surface, the only difference between a space curve and a surface mathematically is that points on a space curve are defined by a single degree of freedom, and that on a surface by 2 degrees of freedom. So, obviously the x and y here are two independently changing variables with no relationship whatsoever between x and y, and the only other relationship which holds true here is that z equal to f x y. That means z is dependent both on x and y's independent variation, okay, but in a way z is constrained by a certain value of x and a certain value of y, okay. So, therefore, you have a 2 degree of freedom system here that we are talking about, and usually an arbitrary surface is defined in x y with a functional relationship x y by an x y grid with p1, p plus 1 and q plus 1 control points. Something like this is what a surface patch would expect it to be, or what it would look like to be. So, obviously we can also, just as we made parameterization of the explicit functions of the earlier kind in case of curve, we added a variable t, so that the local variation of t would lead to a sort of local domain in which you could more closely study a curve of a complex nature. In this case also a surface can be very closely studied for given a global domain of that surface, by just having, instead of one parameter, because there are 2 degrees of freedom, 2 different parameters, okay. So, just as in the curve case, 2D curve case, one was an independent variable and was a 1 degree of freedom system, we were using one parameter t to define the x values, and y would automatically get defined by a functional relationship as the x varies, okay. In this case, because x and y are independent, so we have to consider one parameter t probably in one of the directions, maybe y, another parameter x in the directions of s in the directions of x, so that both independently can vary to have that independent local domain variation given a global domain definition of the particular curve. So, in this case again vst, again we call these two parameters s and t, one and actually x and another representing y, can be defined as xst, yst and zst. So, in case of s, the s varies between some minimum s and maximum s, and so does the t varies between minimum t and maximum t, and x, y and z are functions of two parameters s and t in this particular case. Let us look at a problem to have a more appropriate definition. So, we have been given a set of 4 space points, and the tangent vectors at those points are also given. So find the equation of the Hermitian surface path. So we want to construct a cubic polynomial based fit, but now it is a surface fit rather than a curve fit. 4 corner points have been given as 0 0 1, B 0 2 2, C 4 2 3 and D 4 0 4. The tangent vectors at the corner points are 1 with a magnitude of 1. So the cross vector slopes are assumed to be 0. Okay. There is a requirement of a cross vector slope, meaning thereby the variation of a parameter with respect to S and then with respect to T. So it is a double slope that we are considering there. So we call it cross slope. Okay. So as you see, as the equation evolves, these will automatically come into picture, and so we have to find the basic equation from transformation and formulate the surface. So see the level of complexity which is involved in this particular calculation once we start doing it. Okay. So obviously, if I look at this equation, I would be able to write the vector VST as two different independent parameters. So I say there are two parameters, one is I and one is j, and one is actually on one variable S, another on another parameter T. Okay. So I call I equal to 1 to 4, sigma j equal to 1 to 4, a I j s to the power of I t to the power of j. So if I compare it with what we had done before, we were talking about a case when we just represented one parameter. So basically we talked about, let us say, the point V as a function of t, and we defined a cubic polynomial a0 plus a1t plus a2t square plus a3t cube. Okay, so this was a two dimensional curves case that we were defining. Now we have a surface case. So obviously this t is having another parameter introduced s, and then there has to be, just as you had a sort of index order I equal to 0, I equal to 1, I equal to 2 and 3 in this particular case, we will have to have one index order for t and the other for s, because now it is sort of a multiplication between s and t which would be able to. So we are talking about VST. Okay. So obviously if I spread this out, I would have formulation a11 plus a12t plus a13t square plus a14t cube, and plus a21 plus a22t plus a23t square plus a24t cube into s. Okay. That is how I would like to vary the s's and the t's here, just expanding this particular equation. Okay. So I combine all the s subscripts corresponding to s equal to 1 and all the other values which are therein and put it together in a bracket like this. Similarly, s to the power of 0 I put here, and similarly I do for s to the power 2 and 3. So I have a31 plus a32t plus a33t square plus a34t cube times of s square plus a41 plus a42t plus a43t square plus a44t cube times of s cube. Okay, where s varies between 0 and 1 and t varies between 0 and 1 again. Okay. So there is a local variation in s as well as t, both the variables. So this is how the cubic polynomial is constructed in this particular case. The only difference here is there is an additional degree of freedom, because of which an additional subscript is also coming into picture for the various i's and the various j's along the parameter s and t. So obviously in a similar kind of a manner, you can actually represent this in terms of a matrix equation where R can be VST, and this can be represented as 1 s square s cube 1 matrix times of some A matrix which is corresponding to Aij, and obviously on the other side you have a T matrix, so 1 t square and t cube. So this is how you can write the whole expression here, and this is a 4 by 4 matrix which can vary between A11, A12, 13, 14 and so on to 21, 22, 23, 24, and this goes all the way to 31, 32, 33, 34, so 41, 42, 43, 44. Okay. So this is how this matrix has been realized, Aij matrix has been realized. So, while doing the transformation, you can have a similar kind of a transformation equation. This is a 2 parameter system, of course, and the equation in this case can be in a similar manner as we had done before for a single parameter. If you may remember, so in this particular case, in the one dimensional case, if you just look at it, the final transform matrix was something like a T matrix 1 T, T square, T cube times of some kind of a basis matrix or M matrix, which was formulated. This we had 1 0 0 0 0 0 1 0 and minus 3 3 minus 2 minus 1 and 2 minus 2 1 and 1, and then on the other side we had V 0 V 1 V dash 0 and V dash 1. Okay, so in a similar manner in this particular case, because now the parameter has changed from only T to 2 parameter system T and S, the equation would get slightly modified in this particular case, and here the equation turns out to be a basis matrix M, okay, and there is a matrix U here which corresponds to the S matrix times of a basis matrix M, which is a conversion matrix really in terms of some numbers, okay, times of the A matrix, which is again represented here very beautifully as A11, A12, so on and so forth, times of the transpose of the basis matrix M, okay, times of V to the power of, or V matrix to the power of T actually, or transpose of V matrix. So, I will just let you know what all these transformations mean. Just as you had done here, there was a T matrix. So, here this U is basically the S matrix. I will have this as 1 S, S square, S cube. Similarly, just like this T matrix here in the one dimensional case, and there would be a V matrix here, which is again the transpose. So, basically it is the T matrix that we are considering in this particular case, which is something like 1 T, T square and T cube. Okay. So, this is the V transpose. So, it is really the T matrix, this is S matrix, and obviously the A matrix has already been defined here. Okay, what are the A matrices? And M is the basis matrix, which is really the list of numbers. You remember there is a list of numbers here which relates the T to the different points V0, V1, V dash 0 and V dash 1. In a similar manner, this M is the basis matrix for this particular problem in question, and that actually happens to be very well recognized. Okay. And I will just give you the value of the M matrix in this particular case. So, the basis matrix M matrix comes out to be 1 0 0 0 0 0 1 0 minus 3 3 minus 1 minus 1 twice minus 2 1 and 1. Remember, we have not found out what is the A matrix in this particular case, okay, and the A matrix in this particular case comes out to be equal to, in terms of, so this A matrix was really, if you may recall, the A1, A2, A3 and A0, they were really in terms of these points and cross slopes. How that is how we incorporated the A matrix here. So, obviously, this A11, A12, they should be solved for this particular equation that has been illustrated in this 2-dimensional case problem, this particular equation, okay, and in terms of the available slopes and the available points. And if I calculate what is this A11, A12, A13, so on and so forth from the calculations, it emerges to be the following. So, the A matrix finally in terms of the points and the slopes comes out to be equal to the point V00. That means this is the beginning point, probably one corner of the particular surface patch that is in question, V01, okay, which is the other corner, the other extent where only one parameter has varied, the other has not. So therefore it is corresponding to x equal to 0, probably s equal to 0, and only the parametric variation of t from 0 to 1. Similarly, V10, that is the fourth, the third corner, and V11, which is the fourth corner. So if I am talking about some kind of a surface patch like this, so these four corners are really the V00, V01, and here it is V10, and this is V11. So these are the four corners. Obviously these points have been given in the arguments of the questions, and then there are the various slopes with respect to the t direction. So you have slopes at the point 00, slope at the point 01, slope at the point 10, and slope at the point 11. That is how the A matrix has been formulated. Okay. And the slope with respect to s, now this was with respect to t, which meaning thereby d by dt of that particular function. Now this is the d by ds of that particular function. Obviously there are two parameters, so there has to be a derivative in t and a derivative in x. Both the parameters should have derivatives or slopes along their own directions. So this can be represented as Vs00, Vs01, similarly Vs10 and Vs11, and finally these four parameters happen to be very interesting. These are the cross slopes, meaning thereby these are the derivatives with respect to t with respect to s at the point 00, the derivatives with respect to t with respect to s. So basically this is nothing but d by or d2 by ds dt. Okay, that is how you are basically derivatizing this particular, or finding out this slope with respect to the function there. Okay, and this is at the point 01, and similarly the cross slopes Vst at the point 10, the cross slopes Vst at the point 11. That is how it has been indicated here. And obviously from the question itself you can find out that the four, if I just go back to the question, it has briefly mentioned that the 4 points are given here, probably corresponding to V00, V01, V10 and V11. Okay. And the tangents at the corner points are all 1. So with respect to Vs or t, they are all 1, and that with respect to the cross slopes, meaning thereby with respect to s with respect to t, the cross slopes, they are all zeros. Okay. So I am going to now change this equation into something which is more realizable and say that the particular case that we are considering, this actually becomes now the points, let us say V00, V01, V10, V11, okay, and all these quantities are unity because they are the single slopes, and all these 4 quantities are zeros because they are the cross slopes. Further, this can be represented as the point A, which is 0, 0, 1, okay, B which is 0, 2, 2, and obviously 1 and 1 would remain there, and V10 is corresponding to the point C 4, 0, 4, and D is corresponding to the point 4, 2, 3, 1, 1, and here you have both the single slopes and the cross slopes. That is how the matrix based calculation has been done, just in an identical manner as we did the one dimensional problem. Okay. And so now very interestingly, if you put these different values, so there are actually 3 matrices emerging out of it corresponding to the x values of the points, the y values of the points, and z values of the points. You will have a computational basis with which you can quickly compute the, by putting the transformation equation, which was represented here very clearly as Vst equals U m a m transpose V transpose. Okay. So I am going to now do this particular calculation in the next slide and try to plot it and see what happens. Okay. So you have the formulation represented as the matrix U, which is 1 s s square s cube times of the basis matrix, which has been already calculated as 1 0 0 0 0 0 1 0 minus 3 3 minus 2 minus 1 twice minus 2 1 1 times of the A matrix, which is now assumed to be in 3 different forms. So, I just consider the integrated representation here A 0 0 1, B 0 2 2 1 and 1, similarly C 4 0 4, D 4 2 2 1 and 1, and then you have 1 1 1 1 and 0 0 0 0 times of the A matrix, which is again so this is the, I am sorry, this is the A matrix times of the M transpose. Okay. So, the M transpose happens to be 1 0 0 0 and this goes as 0 minus 3 2. Similarly, this happens as 3 minus 2 and 1 and 0 comes here, and similarly minus 2 minus 1 1 and 1. This is how the M transpose is obtained times of the matrix 1 t t square t cube. Okay. So, the whole question here is now if you vary the value of S between 0 and 1, and so do you vary the value of t between the same 2 domains. Maybe in this particular case the S is equal to half in one case, 1/4 in another case, 3/4 in another case, and so is the values of t here, and you can find out by varying the different parameters in a similar manner. You remember we plotted the Bezier or any other curve before, we obtain this particular surface based on the various values of S's and T's. Okay. And that is how the patch can be formulated. Mind you, here also in a similar manner, if you would have varied the slopes etc. of the patch, then it would be very worthwhile to have variety of topologies emerging in the surface based on the end slopes or end cross slopes variations, and that would be giving us a flexibility to fit again the surface patch on the actual surface that we are actually doing in question. So, I think we have done more or less all what is needed to understand from a curve to a surface in terms of the coordinate processing or the computational exhaustiveness of the whole process. The other idea is how to translate all this information into a CAM package now, and so I am going to now slowly talk about issues related to that following this module. So, this module is now coming to an end. Thank you very much.